This next one will either help understand more or make it more confusing. The velocity function in meters per second is given for a particle moving along a line. That velocity is v of t is equal to t squared minus 2t minus 3 for t going from 2 to 4. We're going to find two things: the displacement and the distance traveled by the particle during the given time interval. Let's talk about how these two things are different, and then we'll talk about how it relates to the net change theorem. Let's suppose that we have a mail carrier who starts at a particular point. I'm not even going to label a number here. Our mail carrier starts at a particular spot and walks down the street, let's say to a corner, turns around, walks back up the street, and then continues past their starting point. Oh, now I need some numbers. Let's say that our mail carrier walked 40 feet down the street and then turned around, walked the 40 feet back, and then walked an additional 15 feet and then stopped. This person's displacement is 15 feet. That's where this person ended compared to where they started. So displacement only takes into account starting point and ending point and their relative positions to each other. Let's suppose that we call right positive. Then we would say that this person's displacement is 15 feet in the negative direction. This is related to the net change theorem because displacement is the integral from a to b of v of t dt. Now remember, v is s prime of t, and so it's a rate, right? And all it takes into account is the starting position, so s of b, minus the ending position, s of a. And if this number is positive, then you would think of it like the thing is in front of where it had started. And if this number is negative, then you would think this thing is behind where it had started. So this 15 feet in the negative direction is displacement. But our friend walked 40 feet, turned around, walked 40 feet back to their starting point, and then an additional 15 feet. What happened with displacement was we really thought of 40 feet in the positive direction minus 40 feet in the negative direction. Maybe we didn't think of it this way, but this is what the math did to us, I guess. And those 40 feet canceled each other out, right? Because you go 40 feet, you turn around, you walk back 40 feet, you end up where you started from. And then there was an additional 15 feet in the negative direction. And so the 40s canceled out, and then you ended up with a negative 15, right? So we said 15 in the negative direction. But as far as this person's shoes are concerned, it was 40 feet and 40 feet and 15 feet. And so the total distance traveled was 95 feet. What distance does is it doesn't care if the numbers that we're adding are positive or negative. It turns them all into positive numbers. And the thing that turns all numbers into positive numbers is the absolute value. And so the distance traveled is the absolute value of v of t dt. All this time when I've been talking about position and velocity, I've never said why we're calling this velocity and not speed. The reason is velocity could be positive or negative. It takes into account direction. Now what we're doing is we're taking out the direction part of it by introducing the absolute value. I don't have a tidy way to express the integral of an absolute value. What we're going to have to do is find out where the integrand is negative and work with it from there. Well, let's start with part A, and that's the more straightforward part. We're looking at the integral from 2 to 4 of t squared minus 2t minus 3 dt. Using the power rule for integration, we end up with 1/3 t cubed minus t squared minus 3t, and we're going to evaluate from 2 to 4. Evaluating at 4 gives me 64/3 minus 16 minus 12, minus evaluating at 2 gives me 8/3 minus 4 minus 6. That totals 2/3 of a foot. And so maybe this particle is moving back and forth and it ends up 2/3 of a foot in the positive direction compared to where it started from. For part B, I need to know where t squared minus 2t minus 3 is positive and where it's negative. So first I'm going to find the zeros. And I get t equals -1 or 3. And now I'm going to use a sign chart here. For t minus 3 times t plus 1, if I let t be a number less than -1, then I have negative times negative is going to be positive. And if I let t be, say, 0, then I have negative times positive, and so negative. And if I let t equal 3, a number bigger than 3, then I have positive times positive, and so positive. And this should make sense because we're looking at a quadratic, and we know that quadratics have graphs that are parabolas, and this one opens up. And now if I look at our original integral here, we're going, t is going to go from 2 to 4. So I'm going to integrate over the interval from 2 to 4, and I see that for part of that, the integrand is negative, and for part of that, the integrand is positive. What we're actually going to do is we're going to find the integral from 2 to 4 of the absolute value of t squared minus 2t minus 3 dt. Now I'm going to express that absolute value of t squared minus 2t minus 3 in terms of a piecewise defined function. It's the negative of t squared minus 2t minus 3 when t, I'm only going to focus it on the interval that we're talking about from 2 to 4. So when t goes from 2 to 3, I'll make that a non-strict inequality at 3. It really makes a difference which one is non-strict. But when t is between 2 and 3, I need the negative of this integrand because then I'll have positive function values. And then we have t squared minus 2t minus 3 as long as t is between, again, for the interval we care about, 3 and 4. Just to really bring this home, I'm going to draw a graph of, or I'm going to sketch a graph of the parabola here. I know that my zeros are -1 and 3, so those are my x-intercepts. And then my y-intercept is going to be when t is 0, I have y is equal to -3. And then I know we're symmetric, so the vertex should be about down here somewhere. So I'll just, this is just really for a visual, not perfection. What we're doing with this whole absolute value part is we're taking the part of the graph that's negative, and I see I missed over here a little bit, so I'll just make it look like I got it right. We're taking the part that's negative and we're effectively like flipping it upside down. That was pretty bad. I kind of fixed it. So here, from 2 to 3, I want the negative of the values, which makes them positive. One's going to go from 2 to 3 and is going to be negative t squared plus 2t plus 3 dt. And then the second one is going to be the integral from 3 to 4. That integrand is going to be t squared minus 2t minus 3 dt. So we'll do all this separately here. So integrating using the power rule and then evaluating for the first integral at 3 and then at 2, and then for the second integral at 4 and then at 3, we get 131 thirds or 46.6 repeating meters. And I just realized, I think up here, I said 2/3 of a foot for part A. That's my mistake. This problem was originally given in meters per second, so this should have been meters. So the displacement is 2/3 of a meter, but this thing ended up traveling over 46 meters. It just went back and forth and back and forth, and when it ended, it was just 2/3 of a meter off from where it had started.